Now, the power of reticular chemistry is that one can go in and change the metals. You can go from a metal where, in the case of the MOF that Eugene was using there, that's a zirconium MOF, and zirconium is expensive metal. But we can go in and make aluminum MOF. The aluminum is much cheaper, and so we can design a material, as you would see here. The MOF is the backbone. Here are our aluminum oxide units linked by organic units containing nitrogen and carbon. And these are the water molecules that are diffusing through the pores. Now, how does this MOF do? So we learned that instead of waiting for day and night cycle, we could push the air, just use a fan to push the air into the MOF. And then with solar panel, we could have power to heat up the MOF to release the water. Okay, so we designed a prototype that has basically shelves of MOF, and it's designed in such a way that certain shelves take up the water from desert air while other shelves release it. Okay, and then it's condensed on basically a powered condensation to produce liquid water. Now, how does this MOF 303 perform? So we took 1 kilogram base device to the Mojave Desert, which is the driest desert in North America, and tested it in the desert, okay? And so I would like you to focus on the relative humidity panel here and the water harvested. And I want you to ignore the first point because this is the water that was in the MOF from Berkeley. So that's released, and then this is the amount trapped in the desert. Okay, that's during the night, this is during the day, during the night, during the day, and so on. Now, the amazing thing is that when you look at the humidity during the day, it dips down to almost 7% relative humidity. And you see how even at these very low humidities, the MOF is still harvesting water. So for 1 kilogram of MOF, we can harvest 1 liter of water. Okay, and here's a video of the water dripping down in real time as it's being harvested. This is the device. It's a sort of a homemade device, but deploying 1 kilogram of MOF. And this is Nikita holding the 1 liter of water harvested. Okay, so this device can work over and over again. You can cycle, and like I said, the MOF remains in the device producing 1 liter of water per day under these conditions. Obviously, when we look deeply into how the MOF is working and how much water is going into the MOF, we realized that the form in which we were deploying the MOF does not allow the entire MOF sample to be accessed by water. So we were only using a fraction of the MOF. So in fact, the potential for much more than 1 liter per kilo was great. And the other factor I think that is so important is not only do you take up water very fast. So you see here, let's focus on this purple line. You see that in less than 3 minutes, the MOF is saturated with water from the atmosphere. And in less than 3 minutes, you can remove the water. So this fast kinetics gave us the idea that you can run multiple cycles per day. And so our next generation water harvester, it looks like this, is able to carry out over 200 cycles per day. Okay, and it's in this particular device, it only employs 100 grams of MOF. Okay, so 1/10 of a kilo of MOF, and delivers 4 liters of water per day. So this is a tabletop device, not much larger than a microwave, and is able to deliver 4 liters of water, of pure drinking water, from only using 100 grams of moth that stay in this device for 5 to 6 years, graded for the lifetime of the electronics of the device. So this is just a short video of how this device works. You see, this is a door that opens, air goes in, the moth is inside, and as you heat, later the water condenses and it would be collected down here at the bottom. You see here a puddle of water that is then filling up this bottle. Okay, so like I said, the productivity of this device is 100 for 100 grams of moth. You can harvest 4 liters of water. So we've gone from our handheld device all the way to this pre-commercialization, let's call it prototype. And we like to always talk about the amount of water per kilo. By the time we are here, we are at 100 liters per kilogram of moth per day. But we have not achieved 100 yet, but we have achieved a significant percent of that. I would say right now we're at about 60 or 70 liters of water per kilogram of moth per day. That's real water that you can get every day from just 1 kilogram of moth. So based on those results, one can check the weather conditions in all over the world. And here I'm plotting the driest deserts in the world, the Atacama Desert in Chile. And you see here at the most stressful times of the year, driest time of the year, you're still delivering water. Okay, that's around, let's say 7 liters per kilogram of moth per day. Okay, those are the driest desert. And you can see that in a place like Lanzhou in China, in the middle of China, you can, depending on the weather, you can harvest still significant amount of water in the most stressed times of the year. Kabul, another dry place, you see here significant amount of water can be harvested. And this is Riyadh in the middle of the desert in Saudi Arabia. You see almost 40%, or excuse me, 40 liters per kilogram of moth per day, and so on. You can do this for Baghdad, New York, Stockholm, Los Angeles, London, Mediterranean region, Granada, Rome, Perth in Western Australia, Cape Town, and so on. Okay, so what this is telling us is that because the moth works at very low humidity, I showed you moth VO3 at 7% relative humidity, it can work at all humidities beyond that. And therefore, I think the vision of achieving water harvesting anywhere in the world at any time of the year is becoming real. And if you're worried that we're going to be consuming all the water in the atmosphere, think about this. If we served 50 liters to each person in the 6.7 billion population of the world, we would have only used 0.002% of the water in the atmosphere at any given day. So with these developments, what we are looking at is a distributed process for water delivery. It's mobile, it's off-grid. You can also personalize it to your taste. The water that is produced is pure, so you can use it for drinking or agriculture or household use. And ultimately, my vision is that we as citizens of the world will achieve water independence so that we are not importing our water from other places. So that's basically my presentation, and I just want to conclude by saying that I think we have developed not just new chemistry, but a wide range of materials and applications that are addressing the water stress in the world. And as I said, Jeff Reimer will be talking about how MOFs will address the carbon capture challenge. Thank you for your attention.
The MOF, obviously you explained, does produce pure water. However, would the quality of the air degrade the device, such as dust or grit that you might find in the desert?
Good question, Lo. So the MOF, as you saw, is really a molecular filter. Mm-hmm. And in our case, it only admits water molecules into the pores. Even if you have, let's say, carbon dioxide in there, because water binds stronger than carbon dioxide does not stick to the material. Okay, so that's one aspect to think about, is that if you are in an environment where, let's say, there are gasoline molecules, octane, or that would not fit in the pore. So the pores are naturally filtering water in. The second point is that we have tested the last water harvester prototype that I just showed you without any filtration of the air. And the performance has been maintained over tens of thousands of cycles. Okay, so that does not seem to be an issue. Now, at the end of the day, if you really want to filter the air, there are filters that, such as what you use in your automobile, that could be used. So it's not a major issue.
And there's a couple questions here just about the cost of a liter of water. So I presume that's related to, there's a fixed cost with the device, but then there's also the MOF itself that presumably must be manufactured. Could you talk a little bit about what is the cost of a liter of water?
So many people point to, you see these beautiful illustrations of the MOFs, very intricate, and they look like they're very expensive, okay? I just want to say that the variety of MOFs that could be made, from all the way from complicated components to simple components to even edible components, natural components, is just, it's staggering. The variety is staggering. So you have flexibility in terms of going from, as I did, from zirconium, which was expensive, to aluminum, which is dirt cheap. Okay, so that works in your favor. The other thing that works in your favor is that device that I just showed you, once you know how to maximally expose the MOF to the air, then you can get the maximum performance out of the MOF. So that only deploys 100 grams of MOF, 100 grams of an aluminum MOF. Now, how expensive could that be? Aluminum is only $2 a kilo. And the price of the MOF in general, unless the organic linker that you're using is very exotic, scales with the price of the metal. Okay, that's all I can tell you. Because the cost of MOFs is something that is held, it's a secret held by the chemical companies that make it, okay? But that gives you an idea. You're not going to be able to make this possible unless the cost of the MOF is low or negligible compared to the rest of the device. So to answer the question, in terms of right now, in terms of production of water using the device that I just showed you, if you assume that the electricity price is about 6 or 7 cents per kilowatt hour, then the cost of 1 liter would be in the range of 4-5 cents, okay? So it's a fraction of what you would pay for drinking water. Now, if you're thinking that this is going to replace desalination, I don't think that it will anywhere in the near future, but it certainly can provide access to water for drinking and for agriculture in many places of the world.